Hello everyone, welcome to this video tutorial on analysis of simply supported beams in ANSYS Workbench. In this tutorial, we are going to focus on how to apply pin support and roller support in case of modeling of simply supported beams and how to combine UDL with the point loads. Let's go to the learning outcomes of this video. After this video lecture, you will be able to model simply supported beams in ANSYS Workbench. Then you can apply UDL and point loads on beam, and you will be able to calculate deformation, reaction forces, movements in the beam, as well as stresses and bending moment diagram for simply supported beams. Now this is the problem we are going to solve. We have to determine maximum displacement, reaction forces, shear force bending moment diagram, and as well as stresses, bending stresses for this beam structure. So the structure is like that. We have a beam of 8 meter length and it is supported at point A and D. At point A we have pin support and at point D we have roller support. Then we have a point load here of 75 kilonewton at point B, which is 3 meters away from point A, and 50 kilonewton point load at point C, which is 6 meters away from point A, and there is, in addition to this, there is a 20 kilonewton per meter UDL is applied for whole length of the beam. Okay, so let's move to the material properties. So in this particular problem, material properties are not given, and thus we are going to consider structural steel for this analysis. So the properties of structural steels are like Young's modulus for structural steel is 2 into 10 raised to power 11 pascals, and the Poisson's ratio is 0.3. This value is in pascals. Then for geometrical modeling, we are going to consider the total length of the beam that's 8 meters. Cross section of this beam is not given, so we are going to consider this square cross section with a side of 0.1 meter. So this is how it will look like, 0.1 meter side square. So, and for this square cross section, the moment of inertia I is nothing but B into h cube upon 12. So it comes 0.1 to the power 4 by 12, and the value is 8.3 into 10 raised to power minus 6 meter raised to power 4. Okay, so what we are going to do, we are going to model this geometry, and again we will come back to slides. So I am switching to this ANSYS Workbench. So ANSYS Workbench, we have selected a static structural analysis. We are not going to change any engineering data. You can see here this static structural structural steel material is considered here, and the values for Young's modulus is 2 into 10 raised to power 11 and Poisson's ratio is 0.3. Okay, so we'll go to the project again, then we'll open this geometry in a space claim. Okay, so I have already done the thing. Space claim is open here. So in space claim, the first of all you have to click on this layout sketches and you have to go and change the units. So to change the units, you can go to files and space claim options. Okay, I will show it once again. File and space claim options, it will open an option. Then you have to click on this units and change this millimeters to meters. Okay, click on OK. Then we'll change the plane. We need to select XY plane for the current analysis. So to change the plane, we have options here. You can see these are 4 options available, and this second option is for the selecting new sketch plane. So click on this second option, then you can toggle between the planes like this. So this plane is nothing but the XY plane, then this is XZ plane, and this is YZ plane. So we have to select XY plane. After selection of XY plane, you have to make this plane parallel to the screen. So to make this plane parallel to the screen, we call it as a plan view, and it is done by this option. So you have to click on this plan view and this will be oriented to parallel to screen. Now what we'll do, we'll use some functionality, that is pan, and we'll shift this here, and we'll take a line start from origin, and the total length we want is a 8 meter. So instead of 0.707 we'll put 8 and we'll enter. So that's it. You have modeled this beam. Okay, you have modeled this beam. Now you have to click on this end sketching option. Then after this you have to prepare a profile. So profile means you have to prepare, you have to go to this prepare module. We were in the sketch, and you can toggle to this prepare. In prepare we have profiles, and in profiles we have to select this rectangular profile. So after clicking on this rectangular profile, you can see here in this trees we have one new folder called as beam profiles. So if you click on this arrow, you will see this, there is a rectangular profile. Now we have to modify this profile because the dimensions are not as per our requirements. So the dimensions are 0.01 mm and 0.01 mm B and H. So we have to change it to the 0.1 mm. To change it, you have to click on this ruler dimensions and again click on 0.01 and put a value 0.1. So after changing this, you have to change the H also. So put a value of 0.1, enter. Then to see this, you can scroll down or scroll up, then or there is an option of zoom extend. Okay, so now we have this value 0.1, or this half of the value is 0.05 meters. Now we have modeled this cross section. We'll close this thing and we'll go to the design. Now in design we have to access, we need an access to this structure or this tree. To go to this tree, you have to click on this structure. So this tree will be visible here. Now you can see there are only two folders, one is a sketching plane and one is a beam profile. Till this we have only modeled or created a profile. We have not applied this profile to our beam structure. To apply this profile to the beam structure, what you have to do, you have to click on this arrow and click on this arrow again. So you can see this line. So you can select this line and apply this rectangular profile. To apply this, you just have to click on this profile. So this is applied. Now how you can check? You can check this. There is a third folder called as beams, and you can see beam rectangular. Now to see this in actual, you have to click on this display and solid beams. Now if you zoom it, you can see this cross section applied to our beam. Now that's it. After that you have to just make one more setting, that right click on this beam rectangular and create a new component. So click on move to new component. So we have created a component. So that's it in geometrical modeling of this simply supported beam. Now we will open this model. We'll go to this workbench and we'll open this model. Now it says that it's starting mechanical ANSYS. Now we'll go to the slides once again. Now next part is the meshing. To mesh, yeah, it's open. First we'll see the slides. So the size of the elements we are going to consider 1 meter per element. So 1 meter per elements means there are total 8 elements in the beam. Okay, and type of element is beam 188. So if you want to see the more details of this beam or element type, you can always have an access to ANSYS documentation. Link will be given in the description. Now this beam 188 element have 6 degrees of freedom at each node. Okay, so we'll go to the meshing. So once check all these things, Yeah, we have imported the geometry. Geometry is component, beam one rectangle, then material is static structure, structural steel. Okay, and you can see all the properties here. Young's modulus is 2 into e to the power 11. You can see it here as well. Then we have cross section, a rectangular cross section, and these are the properties. So you can see here the value of I, moment of inertia, is 8.33 into e to the power minus 6 meter square into meter square. So this value matches with our calculations. Okay, so that's well and good. Then we'll go to meshing. Right click on mesh and click on insert, then go to sizing. Click on this sizing, then you have to select this bar and select on apply geometry. Then after application of geometry, as we have to define the size as well, I have used this element size, or this by default this is element size and size is 0.3 meters. Now to change this, you can directly change to 1 meters. So or otherwise what you can do, you can switch to number of divisions and we will do 8 divisions. So either way you can perform this meshing. Okay, then after specifying this number of divisions, you can go to mesh and click on generate mesh. So you can see here we have 1 2 3 4 5 6 7 and 8 elements. The next part is to apply the boundary conditions. Okay, so the apply boundary condition, the first boundary condition is that we have to apply pin support, and to apply pin support we have to restrict these 5 degrees of freedom for this node 1. So what are these 5 degrees of freedom? We have to restrict x displacement, that is this, then y displacement, that is displacement in this direction, and z displacement, displacement in z direction. Then we have to restrict the rotation about x-axis, so this rotation will be restricted, and this rotation will with respect to y-axis will also be restricted, and only z rotation is allowed or permitted. So to model this, we will go to ANSYS again, ANSYS mechanical, and right click on static structural, insert, and we have to apply a remote displacement. So click a remote displacement, click on this. Okay, now you have to go to the vertex selection method and single select and this. So you have selected this vertex, you have to apply a remote displacement here. Okay, that apply. Then you can see here there are 6 degrees of freedom, and you have to restrict all the 5 from x, y, z translation to y rotation. So to fix this, you have to just put it 0 here. Now this rotation about z axis will be free. Okay, then we'll go to the next boundary condition. The next boundary condition is roller support at node 9, that is end B. Okay, so for this condition, what we have to do, we have to restrict y displacement, z displacement, x rotation, y rotation, whereas x displacement is allowed, because as this is a roller support, this direction, in this direction displacement will be allowed. So this is x axis, so x displacement is allowed, and I will say this is allowed, this is not allowed, this is not allowed, this is not allowed. Okay, again z rotation is allowed, z rotation is allowed, z displacement is not allowed. Okay, so this we have to apply. To apply this, we will go to the ANSYS and we'll right click on insert, and we have this simply supported option. You can directly apply this simply supported option. Okay, or you can apply a remote displacement. So we'll try with a remote displacement first. If it works, this then it is well and good, or we'll switch to simply supported. Okay, to apply a remote displacement, you click on this remote displacement, then click on this edge and select. Then we have to restrict y component, z component, x component, and x rotation and y rotation. So these two are free. Okay, now after that what we will do, we'll apply some UDL. So next thing is we have to apply UDL. Okay, so these are the forces. We will apply UDL of 20 kilonewton per meter over a full length. So okay, to apply 20 kilonewton over a full length, now we'll go and insert. To apply UDL on a 1D element or 1D beam element, you have to click on this line pressure and you have to select this edge. Just after selection of this edge, you have to click on OK. Then define by components, and we have to see here minus 20 kilonewton. Now we have done all the required analysis, minimum analysis, as we have to test this remote displacement type 2 is it will work or not. So for that purpose we will restrict ourselves to this settings for time being, and we'll apply one directional deformation on y-axis to just check is it correct or not, and we'll try to solve this problem. Yes, so it works fine. Okay, so it works fine, and we are getting some displacement of 0.63225. Now what we'll do, we'll modify this setting and we'll apply some forces as well. Now we have to apply the point loads. Okay, we have to apply the point loads. We'll go to next slide. Now we have to apply this 75 kilonewton force at point B, which is 3 meters away from the point A. Okay, so we'll go to this thing. Now to apply this point load, as we have not modeled this beam in a 3 section of 3, 3 and 2, and this is whole one section, so you cannot use this force because this works only on vertices, and we don't have vertices other than A and B point. So to model the vertices, to model this point load, we have to use this nodal force. And to use this nodal force, I will show you, you have to create some named selections. So name selection, until and unless you create a name selection, you cannot apply this. So what is name selection? We just have to select the nodes and make a selection before applying the load. So how to do that? Let's say these are the mesh. This is the mesh. We have node 1, 2, 3, 4. At node 4 we have to apply 75 kilonewton because this is 3 meters away from the node 1 or point A. So what we will do, we will click on this node selection. Okay, and I will select this node and we'll go to this model. Click on this model. Again this context model will be opened here. Okay, go to this module and click on this named selection. So as soon as you click on this named selection, this will appear. Okay, and here one more folder will be added, name selection. Selection is not performed yet. Okay, so to select, you have to go to this node selection, click on this node and apply this here. So what will happen, you can see here the selection will appear under this name selection folder. Now I will rename this to 75 kilonewton. Okay, this should be kilonewton. Okay, now we have to make one more selection here, and what we will do, we'll just click on this name selection. One node is already selected, this has already been created, and we just have to rename this 50 kilonewton. Okay, now we have created the named selection. Now we'll go to this nodal force and we'll just select nodal force of 75 named selection. So it will be applied here, y component will be minus 75 kilonewton. So 3 zeros, yeah. So yeah, that's it. This is how you can add the nodal force. Again we will add one more nodal force. If you don't see this nodal force, you just have to click on this arrow and you can see it. Okay, then again create a named selection of 50 kilonewton minus 50,000, that is 50 kilonewton, and that's that. So we have applied all the forces. Once again we'll try to solve this or evaluate the results. Solve. So this is the warning, it doesn't have to worry about this, and we have solved this. Yes, so we got the result. That's value is 1.2912. Now we will go to the slides. Okay, so we have to calculate the maximum deformation, and these are the analytical results. So if you solve this with the any traditional method using strengths of material, deflection, calculation of deflection for simply supported beams, and you don't have these material properties as well as cross section properties, then you will end up to this solution. Okay, you will end up to this solution, and the values are minus 2164.7. so this w is at x is equal to 4. So we have value of this minus 2164.7 divided by EI into 10 raised to the power 3 meters. So if you do the calculation, E is this, I is this, and into 10 raised to the power 3, you'll get the analytical result 1.29. This will be minus, this will be minus, as this value is minus. Okay, this is minus, so this will be minus 1.29882, and we have the result of 1.2912. So we got an approximate result. This is in pretty in agreement with the analytical results. So we'll move forward to the next type of results. So sorry for that thing. So we want force reaction. We have to check the force equilibrium. So to check this force equilibrium, okay. So what I have to do, I have to show you the results. Yeah, for that thing what I will do, I will open this problem here. All bookmarks. So not this one, not this one, not this one. Yeah, how to calculate the beam deflection. So we have considered this problem. Okay, so this problem we have considered, and VA, so reaction force at A is 139.375 kilonewtons, and at a D it is 145.625 kilonewtons. So to check this thing, what we will do, we'll add insert. We'll go to solution, right click on insert, then click on insert, then we'll go to this probe, and we will add force reaction. So to see the force reaction, where we have to see this force reaction, at end 1 first. So the boundary conditions, we have to select remote displacement 1, then again we have to add one more, sorry not here, one more reaction, and we'll say this. Now you can rename this as well, force reaction A, and this is force reaction at point D. Okay, so we'll solve this thing, evaluate all the results, and you can see the values. So the value of this force reaction at A is 139.3937 into 10 raised to the power 5. So this is in agreement with this value, 1.3937 into 10 raised to the power 3, that is correct. So if we check the force reaction at D, that is 1.45 into 10 raised to the power 5. So this is again correct. So we have validated our results, whatever available analytical results with the whatever analytical results available with us. Now next thing is we have to calculate the bending moment diagram and bending stresses. So to calculate the bending moment diagram and bending stresses, if we solve this thing, insert and coordinate systems, so sorry, we have to go to the beam results, then this bending moment is there, transition moment is there, and bending moment diagram is there. So you have to click on this thing. Now it says that you have to define the path. You want a path and we don't have any path created. So to create the path, you have to go to this model, click on this model, then we have this model here, and at this last we have construction geometry. So in this tab of prepare we have construction geometry, and if you click on construction geometry like this, it will open this 4 options, and the first option is path. Click on this path, so this path will appear here. Now to create the path there are several options. There is 2 point, then we have edge and x-axis intersection. So we'll select this edge option and we'll click on this whole beam. Now that's it, we have to apply this geometric selection and we have created this path. So this path starts at 1 and ends at 2. So this path is required to create the total shear force and bending moment diagram. Now we'll click on this total shear force and bending moment diagram and we'll select this path. So as soon as we select this path, this will be open. Now you just have to evaluate this result. Yeah, so we are at just do this thing. Okay, so this is the bending moment diagram, this is the total displacement, then this is bending moment, and this is shear force. Now if you want to cross check this bending moment diagram with the analytical one, so you have this thing, deflection, and so this is the deflection profile and this is the bending moment profile. This pretty much is similar with our results. If you want to check the values as well, yeah, so the value you can see here, value at 4 is minus 2.16471, and if you divide by EI we will get this value 1.29. so this is 1.29 at 4 meters. Now what we have to do, we have to check the stresses. Sorry. Now we'll go to solution, insert, beam results, and beam tools. Now to check the bending stresses you have to click on this beam tool. Now beam tool, after creation of beam tool you will see that there are more than 3, there are 3 already results components are there, but there is no bending stress here, so you have to add this using right click, insert, beam tool, stress, and minimum bending and maximum bending. So these minimum bending and maximum bending values are nothing but the equal and opposite values. Okay, so I'll explain this once I get the results. Okay, so we have this directional deformation, that is, then we have bending moment diagram, then we have direct stress values are, you can see here, minus 1.27 and 1.25, 1.26. so if you see the combined stresses, minimum and maximum, we are interested in minimum bending stress. So the bending stress here is at the end it is minimum, and at the center it is minus 1.9687 into e to the power 9. Now if you check this maximum one, the same value will appear, but the signs are reversed. Now why this happens? Whenever we do a bending, the sagging occurs in case of simply supported beams, and upper layer of the beam will be in the compression and the lower layer of the beam will be in the tension. Now this minimum bending stress, that is negative stress, shows the similarity with the compression results, and this is maximum bending stress is analogous with the tension results. So if we model the simply supported beam with a 1D analysis or 1D beam 188 elements, using these elements, beam 188 elements, we have to bear with this results that we will not going to see actual compression and tension results. Okay, so these values will be there. If you solve a 3D beam problem, this value will resonate with the results what we will get after the 3D beam analysis, but yes, you cannot see them all together, bend, compression and tension in one figure. So that's it in this video. Okay, is it anything I'm losing? So deformation we have checked, then probes movement reaction you will get 0. Okay, you can solve it, because yeah, we'll check at one result only, one end only. So yeah, we have values -13, -13 and 0. So these are nothing but zeros only. 2 into 10 raised to power -11, 2 minus 2 into 10 raised to power -13, sorry, -13 -13. So this is negligible. Again, if you check probe result, movement reaction, and we want add remote displacement 2 and I will retrieve this result, you can see here values are cancelling each other. No, there are different values, but yeah. So this is again -13 and -13, 10 raised to power -13. This is negligible because this we have not restricted the rotation of both the ends, at both the ends. So these 2 degrees of these degrees of freedom at both the ends are free, so we are not going to get movement reaction. But yes, we have restricted the translations in y direction, so we will get the solid values of force reactions. Yes, A and D. So that's it in this video. Now what we will do, yes, if you want to download the results, you can always use these images and image to clipboard. Now if you want to set this thing, you can set it like this, and yeah, if you want, so this will look good. Okay, copy, and you can paste it whenever you want, wherever you want. Sorry, I'll add more slides here and I'll paste it, or in case of this I'll paste it here only. So these are the results. Okay, so the value here is 1 point. This I will add a minus sign as well now. So -1.29 and -1.29. So this concludes this video. Thanks for watching this video. I'd like to thank all of you to watch this video. I'll say that if you like this video, please click on like button and share this video with your friends and colleagues and subscribe to the channel. Thank you.